Hello, welcome to this session of Jemason tutorials. In this session we focus on series and sequences. There is this question of Further Maths June 2020. Due to popular demand, I've decided to make a video on it. The question says a sequence un is defined recursively by u0 equals 1, u1 equals 3, and un plus 1 equals 3un plus 4un minus 1. Find u2. Roman 2. Show that un plus 1 minus 4un equals negative 1 to the n into u1 minus 4u0. Roman 3. Hence, express un plus 1 in terms of un. Show that Roman 4, un is divergent. Roman 5, un is greater than or equal to 1 for all n elements of natural numbers. Roman 6, un is increasing. Two other sequences, Vn and Wn, are defined by Vn equals un plus un minus 1 and Wn equals un minus 4 un minus 1 for all n greater than or equal to 1. Roman 7. Show that Vn and Wn are geometric sequences. Roman 8. Express Vn and Wn in terms of n. Hence or otherwise express un in terms of n. Okay, we begin with Roman 1. We are asked to find u2. u0 and u1 have been given already, so u2 is easy to find. Replacing every n in the recursive relationship by 1, we can get an expression for u2, which should then be that u2 equals 3u1 plus 4u0. And doing the substitutions, we get 3 into 3 plus 4 into 1. That gives 9 plus 4, which is 13. In Roman 2, we are asked to prove that un plus 1 minus 4un should be equal to negative 1 to the n into u1 minus 4u0. So the proof, we're obviously going to start with the left hand side since we have an expression for un plus 1 given in the question. So un plus 1 minus 4un equals, I replace un plus 1 by the expression given, which is 3un plus 4un minus 1, then minus 4un, the last term. This gives, we have 3un minus 4un, they are like terms, so it gives negative un plus 4un minus 1. Anytime you have a proof of expressions like this, it is always good from every step. Each time you write a step, you go back to the proof and see whether something in the relationship can help give an idea. And it's actually what is happening. You can see this expression un plus 4, negative un plus 4un minus 1. The expression in the brackets of the proof on the right looks like it. So if we factorize negative 1, actually we would have negative un divided by negative 1 will give un. Then 4un minus 1 divided by negative 1 will give negative 4un minus 1. And you can now see the identity that is in the expressions. It's actually an expression obtained from this general one when n is 1. Further, when you go to the left, you would see that this expression and this one are similar too. There is un plus 1 minus 4un and then un minus 4un minus 1. So this is a lower term of this one. And so we have another sequence surely showing up here. Further, if you go back to the expression that we are proving on the right, it has the format of the general term of a GP. We usually have first term times the common ratio raised to the power number of terms minus 1 and so on. So this is surely a GP. So we are going to define a sequence an in which the term is un minus 4 un minus 1. And you can then notice that what we are seeking to find the expression is actually an plus 1, the higher term of that, which is given as un plus 1 minus 4 un. And an plus 1 has been given to be negative 1 into un minus 4 un minus 1, sorry. From this relationship we are just from getting here. So we can see that an plus 1 is equal to negative 1 into an, implying that an plus 1 all over an is equal to negative 1. And being a constant, it means that an is a GP with common ratio negative 1, and the first term being, we come here, an equal un minus 4 un minus 1, and so we get u1 minus 4 u naught, and it's actually the term that is in the brackets on the right. So we can now write the general term for an as the first term, which is u1 minus 4 u naught, into the common ratio raised to the power the number of terms minus 1. Since an starts with a1, the number of terms is simply n, and so we get n being the number of terms minus 1. From here, our expression that we are seeking to find is an plus 1. An plus 1 is actually the left hand side of the proof. So if I get an plus 1 in terms of n, then I will get the proof directly already. An plus 1 should be u1 minus 4 u naught into negative 1 to the n plus 1 minus 1. Again, number of terms minus 1. And that gives u1 minus 4 u naught into negative 1 to the n. Therefore, an now can be replaced by the expression, because it was supposed to be un plus 1 minus 4 un, what we are seeking to prove. So un plus 1 minus 4 un should then be negative 1 to the n into u1 minus 4 u naught as required. An alternative method will be to use the method of differential equations, find an expression for un using the recursive relationship, and then working out the left hand side, which should be equal to negative 1 to the n into this other expression, which if you replace u1 by 3 and u0 by 1, you would get finally 3 minus 4, which is negative 1. So the right hand side will simply be negative 1 to the n plus 1. You can still try that method at your leisure time. We move to Roman 3. We are asked to express un plus 1 in terms of n. Express un plus 1 in terms of n. So we take the relationship which is supposed to be un plus 1 plus 4un, or rather minus 4un should be equal to negative 1 to the n into u1 minus 4 u naught, and this is actually negative 1 to the n into negative 1. u1 is 3 minus 4 u1, which is 1, and so 3 minus 4 gives negative 1. And so we make un plus 1 the subject because we have to express it in terms of n. We just have un plus 1 equals, we send negative 4un to the other side, it becomes positive un, and then plus negative 1 to the n plus 1, because negative 1 to the n times negative 1, laws of indices, we add the powers. So this is un plus 1 in terms of n. In Roman 4, we are asked to show that un is divergent. In the case where un is given recursively, like in this question, you can see un plus 1 equal 3un plus 4un minus 1. Once un is given recursively, we seek to find the limit of un, and once it is unique, we can conclude that it is convergent. Otherwise, it would be divergent if it is not unique. So to find that limit, I'm going to use this relationship that we are just from establishing, and we say from un plus 1 equals 4un plus negative 1 to the n plus 1, limit as n tends to infinity of un plus 1 should be equal to 4 times the limit as n tends to infinity of un plus limit as n tends to infinity of negative 1 to the n plus 1. Now it is important to know that as n tends to infinity, un plus 1 and un, they all tend to the same limit. Let's call it L, the same value. So once you have the limit of un, the rest of the terms in the sequence will tend to that limit too as n tends to infinity. We also have that limit as n tends to infinity of negative 1 to the n plus 1 should be negative 1 if n is odd. If n plus 1, sorry, because the power is n plus 1. If n plus 1 is odd, or 1 if n plus 1 is even. So from the analysis, un plus 1 and un all tend to the same limit. We have denoted that limit as L, so I just proceed to replace it, equals 4L plus, as already explained, as n tends to infinity, this expression tends to negative 1 if n plus 1 is odd, and it would tend to 1 if n plus 1 is even. So we can write that that limit has two values, the positive and the negative one. and so L would be equal to 4L plus or minus 1, which implies that negative 3L equals plus or minus 1, and therefore L equals plus or minus 1 over 3. This limit is not unique. If it were unique, it should give one and only one value. So once it's not unique, it's either giving one and only one value to be unique, or it will give two values or more values, or infinity or negative infinity. Any of those situations lead to divergence. For it to give a single limit value, then it is unique, and we conclude that it is convergent. So we say since limit of un is not unique, un diverges. Then Roman 5, we're asked to show that un is greater than or equal to 1 for all n elements of natural numbers. To prove this one, we actually use proof by induction. We start with the base step, the first term of un, which is u naught, and is given in the equation as 1, and obviously u naught respects this condition because 1 is greater than or equal to 1, so this is true. And then the hypothesis step, we're going to assume that un is greater than or equal to 1 assumed, and then use it to prove that un plus 1 should be greater than or equal to 1. So this is the required statements that we're supposed to prove in the inductive step. Required step, I will use this relationship. We have established that un plus 1 is equal to 4un plus negative 1 to the n plus 1. Get this expression, this inequality form, I need to make use of the right hand side. Now we know that un is greater than or equal to 1 from the assumed hypothesis step. So I can build up this term, a relationship having this term. If I multiply through both, I get 4un is greater than or equal to 4. I can call it the first relationship that I need. I also need negative 1 to the n plus 1. 1 to the n plus 1, as we already said, it will either be negative 1, whatever the value of n, if n plus 1 is odd, or 1 if n plus 1 is even. So it means the least possible value of this expression will be negative 1. So we can write that this expression is greater than or equal to negative 1. And that gives another relationship. Now un plus 1 is the sum of these two, 4un and negative 1 to the n plus 1. So I can add them. Follows that un plus 1 should be greater than or equal to. I would have to add because they are inequalities with the same sign, greater than. So when they are greater than, you can add without any fear of contradiction. It's the greater than sign, so you can add the two inequalities on both sides. So un plus 1 should be greater than or equal to 4 plus negative 1, which is simply 3. This implies that un plus 1 is greater than or equal to 3, which is already greater than or equal to 1. And so this is true. Therefore, un is greater than or equal to 1 for all n elements of natural numbers. Roman 6, we are asked to show that un is increasing. To investigate the monotonicity, we simply find the relationship un plus 1 minus un and then see what comes out. Okay, un plus 1 is already given as 4un, so I write 4un plus negative 1 to the n plus 1, then minus un. I need this expression. This should be equal to 4un minus un will give 3un plus negative 1 to the n plus 1. And the least value of 3un is 3, while the least value of negative 1 to the n plus 1 is 1. So we can say that un plus 1 minus un is greater than or equal to the sum of the least values of these two. The least value here is 3, because un being greater than or equal to 1, 3un will be greater than or equal to 3. So 3, then negative 1 to the n plus 1, the least value is negative 1. So it's greater than or equal to 3 minus 1, which is greater than or equal to 2. Therefore, un plus 1 minus un is greater than 0, because the least value of that expression is 2. So it will always be positive. And therefore, un is increasing, because un plus 1 will always be greater than un. In the Roman 7, we have been given two other sequences, Vn and Wn, and we are asked to prove that these two are GPs. We start with Vn. To prove that Vn is a GP, we start with the relationship or the ratio Vn plus 1 all over Vn, which should be, I go to Vn and replace every n by n plus 1. That will give un plus 1 minus un, or plus un, sorry, all over un plus un minus 1. This would give, now un plus 1 is already given in the equation as 3un plus 4un minus 1, and then plus un all over un plus un minus 1. This gives 4un plus 4un minus 1 all over un plus 4un minus 1 plus un minus 1, sorry. And you can see that 4 is common at the numerator. 4 into un plus un minus 1 all over un plus un minus 1. This will cancel. Therefore, Vn plus 1 all over Vn equals 4, implying that Vn is a GP with common ratio 4, and V1 being, V1 should be U1 plus U0, which is 3 plus 1, and that gives 4. Those are the characteristics of Vn. We also need to show that Wn is a GP. To show that, we would again find the ratio Wn plus 1 all over Wn and see whether it's a constant. Wn plus 1, we go to Wn and replace every n by n plus 1. That will be un plus 1 minus 4 un all over un minus 4 un minus 1. This would be, again, un plus 1 is given in the equation as 3un plus 4un minus 1. So 3un plus 4un minus 1, and then minus 4un. All that over un minus 4un minus 1. This gives 3un minus 4un is negative un plus 4un minus 1, all over un minus 4un minus 1. Negative 1 is common at the numerator, un minus 4un minus 1 when you factorize, all over un minus 4un minus 1. This cancels this, and we see that wn plus 1 all over wn equals negative 1, which is a constant. It then follows that wn is a GP with common ratio negative 1, and the first term w1 should be equal to u1 minus 4u0, which is 3 minus 4 into 1, which gives negative 1. So these are the characteristics of wn being a GP. We are asked to express Vn and Wn in terms of n. So Vn being a GP, we should then have the first term into the common ratio into the number of terms minus 1. And that should be V1 into R to the n minus 1. When a sequence begins with V1, that means the first term is when n is 1. Then the number of terms will just be n. And that's why we have this. If it begins with V0, for instance, the number of terms will be n plus 1. So take note of that. This now would be V1 was established as 4. 4 into the common ratio, and the common ratio is also 4. The common ratio is also 4 to the n minus 1. This just brings it to 4 to the 1 times 4 to the n minus 1 just gives 4 to the n. So Vn equals 4 to the n. Then Wn should also be the first term. The first term is negative 1 into the common ratio, which is negative 1 to the n minus 1, because it also begins with 1. The number of terms will be n, and so that power should be n minus 1. And this gives now negative 1 to the n using the laws of indices. Therefore, Wn equals negative 1 to the n. We are now further asked to express un in terms of n, following the results above. So to express un in terms of n, we'll first bring the relationships. Vn is supposed to be un plus un minus 1, and that implies that un plus un minus 1 should be equal to that Vn that we are just from getting in terms of n, which is 4 to the n, and we can call it equation 1. Wn is given as un minus 4 un minus 1. It implies that un minus 4 un minus 1 should be equal to Wn, which we established as negative 1 to the n. So to express now un, we have these two relationships that have un and another variable being un minus 1. So it could be like solving for un simultaneously. And so we seek to eliminate un minus 1. To do that, I will make sure the terms here, the terms in un minus 1 have the same coefficient. So if I multiply 1 by 4, I will get that 4un plus 4un minus 1 should be equal to 4 to the n. And then I add now to un minus 4un minus 1, which is negative 1 to the n. So adding that, we have 5un. These two will disappear, and we have 4 to the n plus negative 1 to the n. Therefore, un equals 1 all over 5 into 4 to the n plus negative 1 to the n. In the alternative method of Roman 8, we are seeking to find or to express un in terms of n. But un is defined recursively, so we can use the notion of differential equations. If we rearrange the recursive relationship, we get un plus 1 minus 3un minus 4un minus 1 equals 0. And this is a relationship between three consecutive terms of a sequence, and the standard form is usually of the form a un plus b un minus 1 plus c un minus 2 equals 0. Once it occurs in this form, we call it the homogeneous second order recurrence relation, and we seek now to find the complementary function, which becomes the solution. That means an expression for un in terms of n. The characteristic quadratic equation, also called the auxiliary equation, should be of the form am squared plus bm plus c equals 0. From the nature of roots of this equation, we can then write the general solution for un. So our relationship again is this, and we can still express in the standard form simply by reducing all the subscripts by 1, so that we have un plus 1 minus 1, which gives simply un minus 3, un minus 1 minus 4 un minus 2 equals 0. It is still valid in this form, and it gives us now the standard form, so that the characteristic auxiliary equation should be the auxiliary equation would be m squared minus, so un gives m squared, the coefficient of un minus 1 is 3, and it gives the term in m, and then the coefficient of un minus 2 is the constant term, which is 4, equals 0. The roots of this quadratic would be, or the factors would be m minus 4 and m plus 1 equals 0, following that m equals 4 or m equals negative 1. Once the roots are real and distinct, We can denote the roots as R1 and R2. When they are distinct, the general solution, which is the complementary function of the recurrence relation, is un equals a r1 to the n plus b r2 to the n. And so un should be a into 4 to the n, r1 is the first root, plus b into negative 1 to the n, r2, which is the second root. From here now, a and b are simply real numbers to be determined. We use initial conditions. u0 is supposed to be a into 4 to the 0 plus b into negative 1 to the 0. And u0 in the question was given as 1. So we have 1 equals a plus b, because 4 to the 0 is 1, negative 1 to the 0 is 1. That gives equation 1. We also have u1 is giving a into 4 to the 1 plus b into negative 1 to the 1, and that follows that 3, which was u1 in the equation, should be equal to 4a minus b. Negative 1 to the 1 is negative 1, so times b gives negative b, and that is equation 2. So adding 1 and 2, we can eliminate b and then get a. It follows that a plus 4a gives 5a, which should be equal to 1 plus 3, 4. And that implies that a equals 4 all over 5. In 1, b should be 1 minus a, and a being 4 over 5, b should then be 1 over 5. Therefore un equals, we now go to the general solution and replace the constants a and b. So the general solution a is 4 all over 5 into 4 to the n plus 1 all over 5 into negative 1 to the n. And we can factorize 1 over 5 to have 4.4 to the n plus negative 1 to the n, which gives again the solution of un as we had in the other method.